Hi, today I will present problem 4 from this year's IMO, where we are given 2023 pairwise distinct positive real numbers x1, x2 up to x 2023. We define for n equals to 1 up to 2023 an to be equal to the square root of x1 plus all the way up to plus xn times the sum of the reciprocals 1 divided by x1 plus up to plus 1 divided by xn. Given that all an are integers, we are asked to prove that a 2023 is greater than or equal to 3034. Taking a look at these numbers, we notice that this one is around 3/2 times 2023. This motivates us to try an induction in the following way, that we try to prove that an plus 2 should always be greater than or equal to an plus 3. So if we assume this to be true for all n, then we can conclude, due to the fact that we know that a1 is equal to 1, by induction that a2n plus 1 must be greater than or equal to 1 plus 3n. 2023 equals 2 times 1011 plus 1, and therefore we can deduce that a 2023 is greater than or equal to 3 times 1011 plus 1, or 3034, exactly as desired. Since this is exactly what we want to prove, it is enough to show that this inequality always holds. So we want to compare an plus 2 with an. Taking a look at the expression for an plus 2, although it is not on the whiteboard here, we see that this sum and that sum appear in it. Therefore, it is a good idea to give them names. I define Sn to be the sum of x1 up to xn, and Tn to be the sum of their inverses. Therefore, we obtain that an plus 2 equals the square root of Sn plus xn plus 1 plus xn plus 2, all multiplied with the same expression for the inverses. We would like to bound this term from below by a term containing a square root of Sn Tn, because that equals to an. Moreover, we can relate the xi terms to the 1 divided by xi terms. All of this should motivate us to use the following inequality that tells us that square root of a plus b times c plus d is greater than or equal to the square root of ab plus square root of cd for positive real numbers a, b, c, and d. It is basically a corollary of the Cauchy-Schwarz inequality that tells us that the sum of xi squared times the sum of yi squared is always greater than or equal to the sum xi yi all squared. Namely, defining pi equal to xi squared, qi equal to yi squared, and taking the square root on both sides yields that the square root of the sum of pi times the sum of qi is always greater than or equal to the sum of the square root pi qi for non-negative real numbers pi and qi. And if we take the number of summons to be equal to 2 here, then we arrive exactly at our desired inequality. Therefore, we obtain that an plus 2 is greater than or equal to the square root of Sn Tn plus square root xn plus 1 plus xn plus 2 times 1 divided by xn plus 1 plus 1 divided by xn plus 2. This equals an plus square root of 2 plus xn plus 1 divided by xn plus 2 plus its inverse. Since we have a sum of inverses here, we can bound it from below by 2 using the AMGM inequality. Because the xi are distinct, these two fractions are also not equal, and therefore we can't be in the equality case of our AMGM inequality. Therefore, this is greater than 2, and therefore all of this is strictly larger than an plus the square root of 2 plus 2, which equals an plus 2. Using the fact that the ai are integers, we directly conclude that an plus 2 must be greater than or equal to an plus 3, which we already know to be sufficient, and therefore we are done.